too badly up to now, but we'll see. Perhaps you're the good group. Perhaps you're the group that actually do it properly. We'll see. Okay. So if I share screen, I'll talk you through. I'm going to find the right one. The various tools. Oh, that's not going well. Go away. Go on. Back to the beginning. Thank you very much. Okay. So the two main practicals for PM278 are effectively one which requires you to do a group assignment. So one is referred to as PKU, or phenylketonuria, and it's a group assignment. But what I'm asking students to do is effectively I've split the report into 3 different sections, and each student submits their 1/3 of the report individually to turn it in by deadline. We'll come on to what those sections are when we get to them. And then there's a second practical called FAME, or fatty acid reflux ester, where you get 1 submission per student. And today's job is to basically talk you through those 2 assessments. So we'll start with the first one. So the first one is development and application of a phenylketonuria assay. So normal times, what we would do is do this in the lab, but basically what I don't give students performance. I don't give them method sections or details of what to do. I give them this introduction and then basically tell them it's their job to design the assay. They have to go off and do it in groups 2 weeks before the practical, so that when it comes to practical, they've designed the assay themselves, and we see if it works or not. So PKU, or phenylketonuria, is a disorder of phenylalanine metabolism, so amino acid metabolism, and it can rise of one of two main issues. The classical variant of phenylketonuria arises due to mutations in the enzyme or gene for phenylalanine hydroxylase. So the enzyme phenylalanine hydroxylase doesn't work efficiently. This is the enzyme required to convert phenylalanine to tyrosine as part of this pathway. And as a consequence of this, you get an accumulation of phenylalanine, and that is found in the bloodstream as well. That phenylalanine basically gets converted to phenyl acetate and other derivatives, and it's those derivatives that accumulate in cells and cause damage to the cells. They mainly accumulate in neuronal cells, and so this is a developmental disorder. It slows down development of children, and so this is one of the diseases we test for in newborn children. There's a secondary new variant form of phenylketonuria, which is derived from the inhibition of the recycling pathway of the co-substrate. So a biopterin co-substrate used in an reaction, and that has to be recycled continually for the enzyme to still behave at its optimal rate. And so if you can't recycle the co-substrate, then you slow down the enzyme, and that again leads to a build-up of phenylalanine. So in principle, the easiest way of testing for PKU is to test for elevated levels of phenylalanine in the serum sample or blood sample. And so the way you're going to prepare to do that is by effectively reacting any phenylalanine in the sample with the enzyme phenylalanine dehydrogenase. That will convert phenylalanine to phenylpyruvate, and in doing so reduce NAD to NADH. And as anyone who fondly remembers PM245 will recall, NADH has absorbance at 340 nanometers, whilst none of the other agents do. So you can monitor the production of NADH by monitoring the increase in absorbance at 340 nanometers. And 1 mole of NADH will be produced for every 1 mole of phenylalanine that's converted. And so by letting the reaction go to completion, using up all the phenylalanine in the sample to make phenylpyruvate, you can measure the amount of NADH, which is equivalent to the amount of phenylalanine in the sample. Okay. So, in doing this, we're going to do a number of things. And some of these things we've covered before, some of the things will be vaguely new. So, first thing we'll do is create a standard curve or a calibration curve. So this is, you'll all be aware, hopefully, is the relationship between known concentrations of phenylalanine and some experimental response that you're determining. In this case, the absorbance at 340 nanometers. So you'll be aware that the x-axis becomes your independent variable, so this is the thing you've got control over. So you prepare different concentrations of phenylalanine, and you react those different concentrations of phenylalanine with the enzyme to produce NADH, and then you monitor the absorbance at 340 nanometers, the observed axis, as your dependent variable. You prepare 5 different concentrations of phenylalanine for increasing concentration. That gives you a standard curve or a calibration curve. Then you can measure an unknown sample, measure the absorbance 340 nanometers, read to the line, and where that vertical line then reaches the x-axis gives you your estimated concentration of phenylalanine in that sample. Or you can simply rearrange the equation line. Now, the accuracy of how you determine that value is going to be based on how clean that line is. If it's a very clean straight line and all the points clearly sit on that straight line, you have less variety or less variation in the determined values. If the points are more scattered and you have less of a clear relationship, you have more ambiguity around that determination and therefore will have a greater error associated with it. So the first thing we're going to do is create a calibration curve where we're going to have 5 different points, different concentrations of phenylalanine. And we're going to measure each of those 5 points in triplicate. So we get some idea of the variability of readings. Okay. So to do this, you would normally then take a stock solution of phenylalanine and dilute it to different concentrations, and then analyze those concentrations by mixing with the enzyme and measuring NADH production. So that stock solution is used to make the analytical standard curve points. What we're also going to do is use that same phenylalanine solution to make something called quality control samples. So these are made in exactly the same way as the standard curve samples, in that you dilute a known solution of phenylalanine to different concentrations. But this time you dilute them to different concentrations than those used in the standard curve. And the idea is that you analyze these QC samples as though they were unknown samples. Okay? You know what the concentration is because you make the QC samples themselves, so you know exactly what the concentration of phenylalanine is in these samples. But you measure them as if you don't know what the concentration is, and then you use the standard curve to determine what the standard curve says the concentration is in those samples. This becomes the back-calculated concentration for those samples. You effectively want the accuracy of that back-calculated concentration to be within 15% of the actual concentration of phenylalanine in samples. If I quickly stop showing this and share something else, and do some more drawing. Okay, so you've got a standard curve with concentration versus absorbance. And you've got a series of standard curve points increasing phenylalanine concentration that you measure, and you use those to create the standard curve. It looks hopefully better than that. The QCs then are samples that you prepared yourself, and you prepare them at concentrations other than in between standard curve points. You have one at the top end, one at the middle, and one near the bottom. And in fact, you measure the absorbance generated when you react those with that enzyme, and then you determine what the standard curve says concentration is in those 3 QCs. And because you know exactly what the concentration is, because you prepared them yourselves, you can tell whether the standard curve is working. And the process of QCs is basically there to validate the standard curve. It's there to make sure that the standard curve does the job you want it to do, and it can be used to accurately quantify phenylalanine in these samples. Back here. we're not going to worry about parallelism, which we're not going to use it. But effectively, if you have to dilute your samples from patients in order to get the concentration of phenylalanine down to a sensible level where it can be read on the standard curve, then effectively you have to do the same thing with a QC value. You have to prepare a QC value with a much elevated level of phenylalanine, such that it also needs to be diluted before it can be run in your standard curve. But we're not going to have to worry about that because all our standards will fit on the curve as it is. So you measure the accuracy, so how accurate each QC reading is, and you want it to be within 15%. Except at low end. At the low end, if you've got a QC just above the bottom end of the standard curve, which is referred to as the limit of quantitation, you can allow a 20% deviation from the true value. So if I go back to that horrible, badly drawn curve, so these values here, you need to be within 15% of what they should be. This one here, which is just above the lowest point of the standard curve, you can allow for 20%. The dynamic range over which the standard curve can be used is defined by the lowest concentration and the highest concentration of your standard curve. So that's the analytical domain. And you can split that analytical domain into different regions. Well, you can go further down, which we'll come back to in a second. But that's the quantitative domain. So each of these QCs has to be within 15% of the true value. Right at the bottom, you can allow for 20% variation. Okay, back to PowerPoint. So the definition, in order to determine the accuracy value for each QC, you effectively take the determined value from the standard curve, take away the theoretical value, the concentration you know that QC has, divide it by the theoretical value, and then multiply that by 100, and that gives you a percentage accuracy. Obviously, the closer that value is to zero, because it can be positive and negative, depending on if the determined value is higher or lower than the theoretical value, the closer it is to zero, the better, or the more accurate the QC is being determined. So this PowerPoint's all on Canvas if it needs to be. We'll come back to that. So you want to analyse effectively 3 QCs in triplicate. So you analyse 9 in total, which we'll come back to. As for the limit of quantitation, this is defined by the point at which the variation is at 20%. So at the low end, you can allow for 20% variation from the known concentration to the determined concentration. As you go down the standard curve, that variation will increase. It's usually better at the high end and less good at the bottom end. So this gives you 3 different analytical areas across your standard curve. Between the lowest standard curve point, and where you have an area of concentration with a variation of about 20%, upwards is your area of quantification. So from the lowest standard point upwards, you can quantify phenylalanine in this case. As you can see, as you go lower and lower in concentration, going right to left, that variation or inaccuracy becomes greater. Once it exceeds 20%, you can no longer properly quantify using that standard curve. And so, but you can see an absorbance change. It's just that the absorbance change is too variable. The CV is greater than 20%. It might be 25%, 50%. So you've got too much variation in the data, but you can still see an absorbance change. And this gives you an area of detection. So you can detect that phenylalanine is present in the sample, but you can accurately quantify it. And then as you go further down in concentration, you get to a point where, although there might be phenylalanine there, such a low concentration is not generating a big enough absorbance change for you to see it. And so the point between these two is the limit of detection. So below the limit of detection, you can't determine an absorbance change, despite the fact that there may be small level or low levels of phenylalanine in the sample. And by definition, of course, this is the most useful region, the quantification domain. Another thing you'll need to think about in terms of standard curves or calibration curves is how linear they are, which you determine with the coefficient of correlation. The coefficients of correlation vary between 0 and 1 effectively. The closer they are to 1, the more linear the curve. But you should always draw the curve to prove linearity. If you look at this data, you can generate a straight line and force a straight line through it, and it gives you a coefficient of correlation. Actually, this data, if you walk through points, is actually a curved line. And so R being 0.99 doesn't necessarily tell you it's linear. You have to draw the curve to show what's actually happening with the data points. And people have done this. They've generated data sets where R equals 0.99 for various reasons, but shown that non-linear data, or variable data in this case, or curved data in this case B, this is a curve, or this point where you've got an outlier, or this circumstance where you've got lots of low concentration values and then one high concentration, generates a linear line between the average of these and that point. So all of these will generate the same R squared value of 0.99, but not all necessarily showing linearity completely well. Okay, so you can do a standard curve, or you prepare a standard calibration curve and run these QC concentrations samples. And the QCs effectively tell you whether your standard curve can accurately quantify phenylalanine or not. Okay, so all the QCs do is tell you whether the standard curve accurately tells you how much phenylalanine is in an unknown sample. We're then going to test whether, assuming the standard curve can accurately quantify phenylalanine, we're going to assess whether quantifying phenylalanine in PKU patients is a good diagnostic test for PKU. So we're going to have 30 individuals, 15 of whom are healthy and don't have phenylketonuria, 15 have PKU, phenylketonuria, and therefore you'd expect PKU patients to have elevated levels of phenylalanine compared to the healthy controls. So we're going to set a threshold where we say, right, anyone with a phenylalanine value above a certain point we think is a patient, and anyone with phenylalanine below that point we think is a healthy individual. Analyze the amount of phenylalanine in these 30 individuals, serum samples, and then and then determine the accuracy of diagnosis. By which definition, that is the total number of patients accurately identified as having phenylketonuria, plus the total number of control healthy individuals identified as not having PKU, divided by the total number of people in the study, in which case this is 30. And by definition is a ratio, so it gives you a value between 0 and 1. And if it's 0.9 or above, then it suggests this is a very good diagnostic test. If it's between 0.75 and 0.9, it still has value, but it's not as good. So you can define how good measuring phenylalanine is as a way of diagnosing phenylketonuria. Okay. So generally, if we're in the lab, we'd prepare a calibration curve, we'd prepare 9 QCs, so 3 duplicates of 3 different concentrations, and we'd basically run these 30 samples. But we're not in the lab, so we're not going to do that. But what we are going to do is develop the actual assay itself. So I said before that we were going to split up the actual submission. So the submission is usually basically I'll get you to write a proforma. What's this? Okay. We're all good. So it's all on the PowerPoint, but if you've got any questions, David, let me know and we'll catch up. Okay, so the submission has 3 parts to it. Students A, B, and C write different parts. So the first part of the submission is basically writing an introduction and experimental procedures. So how to carry out the assay. So basically instructions that you would expect other students to follow. So that's more of the written format. The second part is data interpretation. And the third part is basically just to find the logic used to develop the assay. We'll come back to this once we've done it, perhaps. That might make more sense. And we'll go through that in more detail. Okay, so good news. The first thing we'll do is develop the assay or design the assay. And we're going to do this in groups. And I'll put you into different groups, probably 5 different groups. And we'll go from there. So before we do that, there's certain things you need to be aware of because these will help you design the essay. So you might want to write these down, or they're on the PowerPoint on Canvas if you can access that. Okay, so your PQ test is going to screen for blood levels of phenylalanine. And the first thing you need to consider is that normal levels of phenylalanine you might expect in a healthy individual will vary between 1 and 2.5 milligrams per 100 ml. Okay, so healthy individuals will have some phenylalanine in their blood, but that will vary between 1 and 2.5 milligrams per 100 ml. Anything greater than 2.5 milligrams per 100 ml suggests that that person is a patient or suffers from PKU. The maximum amount recorded, the maximum you would expect to find in the sample, is 5 milligrams per 100 ml. And so that represents your dynamic range of concentrations that the assay must cover. So it must be able to quantify everyone who has phenylalanine values in these two ranges. And you need to be aware of the molecular weight of phenylalanine, which is 165.19. Okay, so that defines the expected values of phenylalanine that we have to be able to assay for. I've put some requirements on the assay. So you can have an incubation period for the enzyme to convert all the phenylalanine to phenylpyruvate, but you can only have 30 minutes for it to do that. So you can have 30 minutes for the enzyme to do its job, by the end of which time it must have converted all the phenylalanine to phenylpyruvate. In doing so, we want the maximum absorbance detectable in the assay to be roughly around about 1. It can vary down to about 0.95 or 0.93 or 1.02 if it wants to, but somewhere in the region of 1 as the maximum reading for the assay. We're going to make the samples up in 200 microliters in 96 well plates, so each reaction mixture can only have a total volume of 200 microliters. So that's your working total volume. And okay, we're going to produce a standard curve and random samples. So far so good? Okay, so you're going to be supplied with some chemicals to be able to do this. So you've got some standard phenylalanine to make your standard curve points in QCs. And you've got a solution which is 50 milligrams per litre of phenylalanine. You've got some enzyme, phenylalanine dehydrogenase, to convert that phenylalanine to phenylpyruvate. And we often measure enzymes in units. So we've got 1.1 unit of enzyme dissolved in 1.5 ml. And we know that it takes 7 units to convert 1 micromole per minute of phenylalanine at the temperature and pH that we're going to use. For the enzyme to be stable, it needs to be in a glycine buffer with a concentration of at least 200 millimolar. We've also got an NAD solution because NAD is the co-substrate, because NAD is converted to NADH, and we've got 1 gram dissolved in 745 ml of water. And we've got some more concentrated glycine buffer, which is concentrated at 750 millimolar. And all these other things are dissolved in water. So we've got 750 millimolar glycine buffer. Okay. So everyone has that information? I'm assuming we're all okay. So things you need to remember. One is that our total reaction volume is 200 microliters. The second thing is to remember that we're measuring production of NADH by measuring absorbance at 340 nanometers, and NADH is a molar extinction coefficient of 6,220 at that wavelength. And we want the assay to roughly cover the range 0 to 1 absorbance units and have a 30-minute incubation period. Okay, we'll see how this goes. So far so good? So we're going to do this by looking at 4 different questions which will help us develop the assay. The first question, we'll do this in breakout rooms initially and we'll see how that goes. So the first question is basically, what is the concentration of the maximum possible level of phenylalanine you would expect to find in the sample? Okay, so if you take the maximum level that we've stated is possible, 5 mg per 100 ml, I think it was, what is that as a concentration? And if we assume we can convert that phenylalanine directly to NADH without adding any other reaction components, just by magic, which is, okay, physically not possible, but let's come back to that in a minute. What would the absorbance be of the NADH produced? And once we know that, we can think about how much we can dilute the phenylalanine by adding the other reaction components to bring the absorbance down to roughly 1 absorbance unit. Okay, so if I stop sharing screen. Okay, then, how many people have we got? Oh, we've got more now. Who else is coming along? 14. Who's here that wasn't here a minute ago? Who's missing?
I joined late, so that might be one.
So I've got 14 people. I can't see 2 people on my list. And oh, I know. Okay, someone who's supposed to be there this morning is turned up this afternoon. Well, okay, we'll go with that, that's fine. I'll make a note of that somewhere. Okay, so I'm going to put you into breakout rooms and leave you to think about that for a short while. I'll come around and talk to you about how to approach it, and we'll see how it goes. So, let me just think how I'm going to do this. Create breakout rooms. Let's give you 5 of them, and let's put people into those breakout rooms. So,